Okay, so we start with second scaling law. I keep saying you scaling means reducing the dimensions. The idea was of scaling was, if you recollect my first few slides, first few PPTs lectures, for all VLSR integrated circuit people, the Moore's law is something like sacrosanct, which it says in 60s that component density will double every year. And since that law has to be followed as if it is something God sent, and Intel's chief has said so earlier, so everyone is trying to follow all over the world Moore's law. How do I get to Moore's law? In 90s, as I said, we couldn't, by 95, 96, we realized that you cannot double every year. So Moore came out with 90 another law, said it will double every 2 years. Then later he said, okay, every 3 years. But the Moore's law still stands. So how do we actually do a design which you have done for, let's say, one technology, let's say for where the channel length was 0.5 micron, and I shift to technology which is 0.25. So do I take everything half everywhere? And if I do so, and it design works because everything is halved by me, okay? That was what we call constant field scaling. Everything can be better off in case it will not be worse anyway. But as I said, this was true, say from 5-fold we could go to 2.5, 3.3 was technology, system people say 3.3. Then we went to 2.1, then we went to 1.5, and of current trends is 1.1 or 1.2. We are going for 0.8 soon, or we have actually chips which are 0.8 volts. And I don't think it will go beyond 0.5 or something, because then the noise will take over most of the times. Which essentially means you can scale the technology parameters by 1,000 times, 10,000 times, billion times, but voltages cannot scale by that much amount. And if voltages cannot scale, then we say we cannot have constant fields, because length will scale down, but voltage will not scale by the same factor. So voltage by length will be larger, and therefore fields will be larger. So constant field cannot be attained. So the design which was done in the last, this cannot be just converted to the next technology by just scaling. So of course we still try as much as possible. This word was used because of that. S is called scale factor, which is more than 1. And typically it is 1.4, which means 1 by 1.4 is 0.7. 0.7 into 0.7 is 50. 0.5 means every time double. That word double came from this. Okay. So the technology was scaled by what we call 0.7 times every time. 65 nanometer went to 45, 45 to 32 to 22 to 16, 11 and 0. Okay. So hopefully that, I don't know, in my time it will reach less than angstroms, but let's see. So in constant voltage what we did is the following. As I said, this is not something which is related to this course specific, but just for the sake of it, I thought, this idea is because, as I say, I realized that afterwards you will never learn devices anywhere. So I thought maybe I'll force through your throat something. Okay. So I say W, L, Tox, if anything else, Xj, all will scale by S. Then VDD, VT, do not change, do not scale. And finally, NA and ND, they will scale by NA square, NA dash. Will not go into detail right now, why? But some other day, those who are interested should come and ask me why this. So under this new scaling parameters, if I evaluate the power or current, the new current ID sat, one can find it is S times ID sat. What was in the case of constant field scaling? It was 1 by S, now it has become S times. Okay, so current has increased, in fact by scaling. And if I do power, since the voltage is not scaling and current is going upwards, So PD sat or PD as you can see, that becomes S times P, because current scaled up but voltage did not scale anyway. So it became S times the power dissipation increased. One of the feature of Moore's law was that if you scale down, as we did earlier, power went down, current, everything went down well for you. But now we figure out if we can't do that, then the advantage of scaling, which was very predominantly power related, was not seen. However, irrespective of whatever we say, one of the feature of scaling you should realize, if you see your MOSFET clearly, let's say N channel is used, it's not that NP channels cannot be used, but just like that, this is your channel length. Let us say V is the velocity with which electrons go from here to here. What is the current? Q and V. J sigma E means Q and V. If V is the velocity, then the time taken from going from source to drain is L by V. As channel length reduces, velocity saturates. We know the electric field larger, the velocity will start saturating. So we say now, if velocity saturates, which is some constant quantity, and you keep reducing channel lengths, then what will happen? The time taken to go an electron from source to drain will reduce. Essentially saying, you are speeding up. Is that correct? You are speeding up, okay. So by scaling, one advantage you will always get is speed advantage. That is why we went for scaling, because we said, okay, if I want to work on a Intel processor at 6 gigahertz, I must have MOS devices which works at 6 gigahertz. The time taken should be enough smaller so that they can allow signal to pass. Is that clear? This was the reason why scaling went on, even if power was not in your favor. Okay, power did increase, but the speed starts improving. And one of the major interest in any circuit which is related to devices, we have three parameters, which I said, which are the three parameters we actually modify, we are looking for optimize. One is the power, other is the speed, and in integrated circuit the third is area. Smaller the area, larger number of devices I can put in same area, so it's called density numbers. So smaller the dimensions, density will increase, speed will increase, but what at the cost of power. So one has, when I design a circuit, I have to figure out what devices sizes I should use or what things I should plan, so that these three are optimized for a given specification. Someone will say, this is my spec. So I have to match something on that. Okay. At first I said, this cannot be done under these specs. Okay. Either you allow me power, or allow me area, or allow lower speed. Otherwise I cannot meet all of it. That's why it's called triangle. Is that word clear why it was called triangle? I said earlier, this is called power, speed, area triangle. You pull one, the other has to reduce, or vice versa. Something you have to give up to achieve something. Okay. This is what essentially designer's job, how to optimize the circuit. Okay. In doing so, he should optimize the device parameter, because that's the only thing which is directly in his control. So he must understand what device works, and therefore he should be able to optimize device performance. Is that clear? So at the end of the day, all semiconductor people are looking for integrated circuits. This is one area of our interest. What is the other area now? Optical devices. We are now looking for all optical circuits, no electronics, photonics. Okay. We'll prefer that. In between what we'll do? At least partially we'll use photons, partly we use electrons, and you say optoelectronics. Okay, so partially here, partially there. So we'll have to now see conversions as well. So maybe next, after my BJT, last part of our course, we'll look into some of the photonic devices like LEDs, lasers, photodiodes, solar cells. These are essentially full photonic devices. And also there are newer stuff, okay, just for the heck of it. There is a chemistry's Nobel Prize was announced some 15 days ago. You know what was it? Crystal, therefore I am interested in. It's called quasi-crystals. Okay, I thought maybe I inform you what is it. We started with semiconductor theory and we say all crystalline materials are possible only in periodic arrangements. They are called crystals. There are only 14 ways in which they can be organized and mostly they will be quadrilateral or triangular. Okay. That means the symmetry can be obtained either if the structure is triangular or quadrilateral. However, this person from Israel, he has figured out in 82 is the experiment in US, that there is some kind of fifth plane noise. If it is hexagonal, it can be repeated. If it is 4, it can be repeated. Because one can put over there, symmetry can be obtained. Periodicity is known. Fifth, you cannot. Okay, because then the one gap will remain there. Okay, so it was figured out that if crystal has to be periodic, the fifth plane will not allow. However, if you rotate 360 degree, 5 times you will get that symmetry again. So this was called quasi-crystal by him. Now the advantage of quasi-crystal is it's insulator for both thermal as well as electricity and therefore can be used extensively for thermoelectric effects. So another power generating device may come which has higher efficiency. It can also be used in LEDs for improving the efficiencies. Blue laser, for example, gallium nitride, when they got it, they didn't realize, but they had actually quasi-crystal there, that's why they saw blue light. Why blue light was not, earlier we couldn't get? Any idea? Okay, that optics will come back to it. The energy gap of a semiconductor, only that much energy I can output out. That means the wavelength is decided by the energy gap. So there was no material which is corresponding to blue. Okay, I can't tailor band gaps. So I can never get blue light which is direct band gap material. I have materials which are indirect, but I could not create a material which was direct band gap of blue light. Therefore blue, but this laser, gallium nitride laser, actually came out with blue light way back and that also got a Nobel Prize. So the fact was that they didn't know that time that they are using a quasi-crystal. Now it has been proved that the property came because of quasi-nature of crystalline material. So think of it, your future is much different from what I am now telling, and don't forget that whatever I taught still will be valid because I am teaching a lot of physics behind. That may be also continued on the devices, circuits, which you will see in the near future. So this whole idea is to bring it to what's happening now, so that you should not feel कि यार ये क्यों बड़ा है, नहीं आगे भी है, दुनिया बहुत बड़ी है. Yes. No. Smaller the time taken, the speed will be higher. In a circuit, current is proportional charge by length, charge by time. So essentially I am saying higher speed I can attain because larger currents are equivalent in shorter time that current I can reach, so that the capacitor as if can be charged faster. Faster charging or discharging means speed is very high. Okay, so having said so you can see that the last part before we quit this area, MOSFET, is the following. Someone should ask us what is the maximum frequency up to which a particular MOSFET can work. Okay. And that frequency of interest, because any other signal you are going to use should be 1/10 of the maximum frequency. This is provided by the MOSFET intrinsically. So it has been found, and that word which essentially is called FT. So FT of a transistor is the uppermost frequency up to which small signal analysis is valid, and MOS transistor or any transistor can be actually utilized. But that is the maximum for all safety measures, that everything else not considered by you, some assumptions made, if you remove them, the best frequency should be 10th of that or at least 5th of that. You shouldn't go to FT, because at FT things will start actually failing. So what is an FT? FT was taken from this fact. Let us say this is my MOSFET. Okay, this is my grounded. There is a capacitance we know very well, input capacitance here. This is equivalently saying you have a gate and you have a CGS. Right now assume this capacitance is negligible. Right now, we can improve later if you need. and then we say, if this is my VGS, GM VGS, and of course R0 is very high, so I can actually remove it, something like this. So we said this is something that means a voltage at the input side which charges the capacitor, and therefore change in this voltage essentially will give you a II current which is CGS, okay, maybe CdV by dt can be written as CGS into VGS, which is AC current. Now this current, we can see, if any change here is reflected here, so what I do is, the current which is flowing in this circuit, AC current for example, I0, whenever this, if I keep increasing the frequency, what will I change? The input current, II, as j omega changes, II changes. When this input current is exactly equal to what is sustained at the output, which is your I0 current, at that frequency we say you have maximum frequency possible. Is that clear to you? What is the definition of a frequency at which II is equal to I0 is called Ft. This is how we define, and that is what I say, j omega CGS into VGS is equal to GM times VGS, or one can say from here, K of course is this magnitude wise, one can say Ft is Gm upon 2 pi CGS. Now this Gm is a function of what quantities? Gm, two way we can write, 2 beta IDS, or what is we can write, beta times VGS minus VT. Is that correct? So for a given VGS VT, because VGS will be fixed by VDD, maximum VGS available to you will be VDD, power supply. For that maximum value of VGS, for a given technology of VT, for each transistor of choice, Gm is fixed. CGS, which is related to the input capacitance, is related to the oxide capacitance. Okay? So the Tox, which is also a parameter of technology. So if you see, if I just substitute the values, if you see, Ft will become only a function of technology parameter and not connected to any, except VGS, which is of course your external control. Otherwise it is decided by the technology, what is the Ft of a transistor. Typically it will be of the order of course, as I said, depends on VGS and W by Ls you use. Typical, if you plot frequency Ft versus omega, it will start saturating at very high frequency because of the other parameters will become function dependent. This may be around 10 gigahertz in most cases. Omega. Oh sorry, what should I plot? Ft is a function of VGS. Okay. Sorry, thank you. So if I at best larger the VGS means it will go to VDD, and by then this will start saturating, and typically 8 to 10 gigahertz of FTs are possible in most MOSFETs unless your channel lengths are extremely low, which is what is going to happen. As channel lengths will reduce, Ft will further increase, and that is the term which I was saying. If the channel length reduces, speed improves because Ft also will go much higher. So 10th of 100 gigahertz will be 10 gigahertz, 10th of 150 gigahertz will be 15 gigahertz. So you can start operating at much higher frequencies for even analog functions, the new devices, with a very short channel. Of course it has its own problems. We'll see those problems little later. I'll just give the values of Ft I obtained. Just do your analysis correctly. This has been found to be equal to mu times VDS or VGS minus VT, whichever you write, VD sat, okay, divided by 2 pi L square. You see the mobility, as your VGS will increase, the mobility itself will get affected. It will go down. Higher the voltages you apply, fields will high, mobility will start reducing. So you can see from here, one of the feature of this term which I am writing here is for a given power supply values, which is what maximum you can get, mu is fixed for your device from the technology side. L is the length of the channel length. So obviously, if you wish Ft to be higher, you should reduce channel length. Smaller the channel length, Ft will be larger. But something which is now going to hurt you, smaller the channel length, mobility itself will go down. Okay. Why? We'll see a little later. As channel length reduces, the fields are so high that mobility does not remain constant. In fact, it starts reducing. Is that clear? So for a given temperature mu being constant, for a given power supply values which is VDD minus VT, the Ft goes inversely as length of channel length of the MOSFET. Okay. This is the uppermost frequency up to which MOS transistor will behave in a small signal model, and therefore amplification is possible. Is that word clear? This is the maximum frequency up to which MOS transistor can behave like a small signal equivalent model, and that's the frequency up to which signal can be amplified. Is that correct? This is the Ft value. So when you start designing a circuit, which hopefully someday you should in the next semester, then you should first look into transistor manual and see what values I have to design and what MOSFET number I should choose, which will give me that Ft value. Okay, I want to work on 100 megahertz, Ft should be at least a 1000 megahertz means a gigahertz. So look for MOS transistor which has Ft of at least a gigahertz, so that your operation at that frequency is safe all the time. Is that clear? This is what search you have to do from the manuals. Okay. Something before I leave the scaling last part we forget. Few things happen in a MOS transistor if you scale. As I say, if you reduce length, this is your VDS, this is your source grounded. The problem which we see here is the following. If this length reduces, EY is very high. Y is this direction, EY is very high. If EY increases, I just say mobility is a function of electric field. Larger the electric field, mobility starts decreasing, velocity saturates. Okay. So first effect is called velocity saturation. Why this affects you? Because velocity saturation, any current, drift current is, if V saturates, you can't increase current unless N is increased. N increase means only N can increase if I increase VGS. But VGS cannot increase beyond VDS anyway, at the maximum VDD available to you. So that means N cannot be arbitrarily increased, and therefore current will start saturating anyway. So the maximum current which you can draw from a transistor will get limited when you short channel it. This word is called short channel. This is the first problem which all of us have faced in our careers throughout so many years. The other problem which is not very obvious to you and which I won't like to discuss too much is Vt is a function of everything including channel also. Okay. And it can be proved, and not this course, Vt will be Vt0 plus something delta Vt. As the length reduces, the threshold rises. So what does that mean? VGS minus Vt will decrease or increase? Decrease means current will decrease. So larger, you thought that you will get pickup higher, but now you are reducing the channel length, Vt enhances because current goes down. Okay. This is the second effect, which I say is the VT effect. And the third and not the least important of them is very serious problem. When the device is in saturation, in particular, the maximum fields occur. Why? Where is the maximum field here? At this point. This is the maximum field point. VDS is, all the time, drop is here, okay. At this point, and if the channel length is small enough and this field is large, electrons acquire sufficient energy. When you have an electron moving in an electric field and electric field rises, they acquire more and more energy, kinetic energy. If they become very energetic, at this somewhere here, when they reach drain side, there is a what we call lucky electron model. We believe some of these electrons have so much this, they can actually tunnel into oxide. Okay. And if they reach, negative charge reach into oxide, what will happen to VT? It will become more positive or more negative? Negative charge in the semiconductor will push positive charges in this. Yes, it will decrease or it will increase, depends on P or N, whatever you are looking. So that means VT will vary as I reduce the channel length. Some carriers will actually get inside the oxide. A interesting device which is shown here does this job and its name is different. Okay, this is first oxide, this is one gate, this is another oxide, this is another gate. This is called EPROM. This is called EPROM. And once the carrier goes into the center part, they cannot be withdrawn because they are floating gate, no connection to the world. So the carrier reach there will shift the VT to some value which may be higher than VD. So for any number it cannot be raised out. So you say stored 1 on that. Okay. You remove no charge is put, you say 0 is there, VT is a normal VT. So we say 0 and 1 stored on a EPROM. Is that correct? Electronically programmable memories are called EPROMs. This is an EPROM which essentially works on hot carrier effect. What is this effect called? Hot carrier effect. Why it is called hot? Because they pick up energy, electron temperature rises, therefore they are called hot carrier effects. There are many more effects, many more interesting devices out of hot carriers. Some other day, some other time. So is that clear? So shorter channel length does not mean good for everything. Shorter channel have advantages, but also associated power dissipation problems, leakage problem, many issues will appear as I start scaling the circuits, devices to 45, 32, 16, 11 and whatnot. Okay. Because if the thickness of the oxide reduces, what is happening across this field? Electric field is very high, tunneling can easily occur. So gate current will flow. Okay. So there are leakages. So channel length reduction is not, or scaling is not the panacea of everything. It does give you some advantages. If you can manage other disadvantages, you can make best use of it. That's what we are all trying last 30 odd years or 40 odd years. Part of us, me, myself, many of us here as well. All over the world there may be around 1 lakh of scientists who only work on MOS devices. Few of them are here as well. So please look at it. This technology is going to remain irrespective of what I am saying today. As I said, 2050 is my ultimate, I said. The reason I said 2050 because I may not survive. And I wish not survive. Not just that I will not survive, I wish not survive. Before we quit this, another small part which I forgot, maybe now I can tell. If this is what a typical amplifier looks. And if I do equivalent circuit, only for the case of DC, right now DC gain. So this is my VGS, this is my gate, this is my source. This is GM VGS. Then this is my R0 and this is my RD which I externally put, this is my R0. So V0 by VGS, which is nothing but V0 by Vin, is equal to the DC gain, which is minus GM R0 parallel RD. or equal to minus GM RD. Why I wrote so? R0 will be typically of the order of hundreds of tens of mega ohms and above. The load which you'll use typically order of few kilo ohms, 10 kilo ohms, 20 kilo ohms. 10 kilo ohms parallel 100 mega ohm, 10 mega ohm is 10 kilo ohms. So typical gain of an amplifier is decided by the load and decided by transconductance, which is function of size of the transistor and the current biasing you did for this VGS minus VT or IDS, whichever you are fixing, that may decide the GM, and this is the external load which you put. Okay. This means an amplifier, small signal amplifier, is a function of IDS, W by L and load. This is DC gain. Why it was called DC gain? Though it is a small signal gain, which has an input signal in fact, still we call it DC. Why? Because frequency dependent terms we neglected. That's why it's called DC gain. Is that correct? It's called DC gain. Though it's not really DC, it's called DC gain. Okay. For most transistor, lambda dash by L is lambda. This value length, if you this will be order of 0.01 or even lower. And lambda VDS term, if this 1 plus hai, if this becomes smaller, the other terms do not have any VDS dependence, it's only through 1 plus lambda VDS. If lambda is small, R0 is very, very high. Typically I said you, R0 is 1 upon lambda IDS. So smaller the lambda. So is that some interesting thing I said? If lambda has to be smaller, what should be for the lengths? Larger the length, channel length, larger is R0. This is very interesting. All digital people kept on saying what? Reduce channel length, reduce channel length. Analog people came and said, nee, I want to have a larger channel length. So this was the first time people realized that if I put analog circuit on a digital technology, then I will be actually punished because you say, I will get 22 nanometers. Okay. I say, but I need at least 0.1 micron. He said, forget it. This is what you have. So when you put analog circuit on a digital hardware, which is called mixed signal, which 99% systems are, the worst analog part is working there. If I separate analog like op-amps or A to D converters, a separate chip, I can do far better because I can fix my length higher. Okay. But if I go on a digital hard world and I have a small area of analog functions to implement, it has to be the worst technology I am facing. That's why design of a mixed signal circuits is a real challenge. There is RF part there, it puts some more inductive problems. So God save you. And okay. That's why the designs are very interesting. Is that Raj clear? Okay. The other part in the same circuit, one can see from here, we are only looking as if we are looking small signal analysis and therefore this, but you can do large signal analysis as well. And let's say my inputs are pulse nature. Okay. Let us say this is my VDD, this is 0 and this is VDD. Is that correct? And I am interested in a characteristics which is called, what is this characteristics called? Transfer characteristics. So for this circuit, I want to know transfer characteristics. When my input signal goes from 0 to VDD, let's say it has a beta or W by L some value, it has some VT which is known to me. Okay. As input is 0, this transfer is switched off. Okay. As input is 0, transfer is switched off. No current in this, no current in RD. It could be 0 here. The maximum value VDD appears here. The assumption is transistor is not leaking. Transistor is off means open circuit. Okay. That is the problem now in newer technologies come, this will leak. Okay, so if 0 volt I get maximum VDD. See the other side, if I reach VDD, how much is VGS? VDD minus VT is my VGS minus VT. Now you can see this is the maximum value I can get, VDD minus VT. That means larger current will start flowing. Larger current means larger drop. If it is larger drop, the remainder part is V0 is VDD minus IDS into RD. But IDS itself is a function of mu Cox W by L VGS minus VT VDS or V0 now, half V0, call it V in, V0 square. So if I reach this maximum, this is tangential equation, you have to solve simultaneously. You figure out that this value may reach a small value which is called VO minimum. Smallest value because this will be highest. This will be highest. So if you solve, the VO will become smaller and please remember, larger the current, more drop across here, the rest remain coming here. Maximum current means maximum drop here, the rest is coming here. In between, when you cross VT, the way transistor will show, this equation is still valid, depends on of course status. Initially when I cross VT, this was close to VDD. Is that correct? Before VT, output was close to VDD. As you cross this V in minus VT is small, very small, you have just crossed VT. Small current can flow. Smaller drop will come here. So this will be slightly, V0 will be going slightly below VDD. So V0 is close to VDD but slightly smaller. This is very small, VGS minus VT. So transistor is in what state? Saturation state. And then if you solve this, so I see a characteristic something like this, of this nature. Is that correct? This is called the transfer characteristics of a MOS inverter. Okay, because you can see if input is low, output is high. If output is high, input is high. Of course it has timing going with it. So it's called inverter, which is the basic element of a digital circuit. Okay. Again, this characteristic depends on what? Can you see from these two relationships on what basis it is related to? Of course, RD is one value, which I can keep higher per se. It is essentially decided by this, but this is technology. I cannot play much. This is maximum VDDs I can use. So all the difference, sharper characteristics I have to do, W by L should be higher and higher. Why I am looking for this kind of, what is the ideal characteristic I should have? This is what ideally I am looking for. What is this called? Switch characteristics. So an inverter acts like a switch, but not close, not very good ideal switch, but close to ideal switch. To make closer, what should I increase? The size. Size means kya bada? Area. Is that clear? Current bada, power bada. Is that correct? So anything I do, what repercussions I get, I must know in digital hardware, because that they are deciding power, they are deciding area. So whatever I do must conform to specs I have been allotted. Is that clear? This is called inverter. Using an inverter, you can replace this RD by another device, maybe this side, and that's very interesting device. This is what we actually will going to use all the time. This is a P-channel device, this is an N-channel device. Input is here, output is here. Is that correct? Now you can see, if input is 0, what is the status of N-channel transfer power? If input is 0, ये 0 है. What is the status of Tn? Tn is off. Is that okay? 0 minus Vt, no channel support, this transistor is switched off. However, look at this side. This is source, this is drain. Why it is called source? Because holes can move from power supply down field wise. So this is the source, current is flowing in this direction. What is VGS for this? 0 minus VDD. For a P channel device, you need negative voltages. Largest negative voltage is available to you for the P channel, VGS. VGS minus VT will be there for maximum. So transistor P is in non-saturation. So this is conducting, but this is not conducting. Is that clear? N channel is not conducting, P channel is conducting. So it can't do anything. So the V0 still remains VDD. As I increase V in, which crosses at least the N channel threshold, and I told you in CMOS, what is the value I keep? What is this magnitude means? P channel VT is negative, so value wise both should be same. It's not necessary but normally kept same. If it crosses a VT value, N channel starts conducting. What is the state? Let's say this is case 1, case 2, Vn exceed Vtn, small excess. What is the status of Tn? Saturation. It was VDD, full VDD is VDS. Please remember this is VDD, which is VDS. This is VGS minus VT, which is very small, just cross VT. So Tn is saturation. But since you have not increased too much here, this still is in non-saturation. So the method of solving inverter which we learn, every time find IDSN is equal to magnitude wise IDSP. Because in a circuit, only one current can flow, okay. The N channel current must be equal to the P channel current. Find the status of transistor of P, status of transistor of N. Write those equations in equate, okay. And then you will get the V0 term among them and you can solve for V0 term in terms of Vn. Increase W. Larger the W value will come closer to that. Is that clear? What will happen if I increase to VDD before I go further, last in between? If this reaches VDD, what will happen to P channel? It will become switched off. So no power supply current can come. What will be this voltage then? This is like a resistance which is grounded. This potential also should be equal, no current. No current means same potential. So at the end of the day, you can find at Vn closer to VDD, output will also go to 0, okay. In between, if I further increase Vn, and that's the most important characteristics in MOS transistor, CMOS. This point, at some input, when I go further, Vn is larger than Vtn, but Vn minus VDD should be closer to VDD by 2. I figure it out, both transistors are in saturation, and in saturation the current, if you write, it is VGS minus VT square. Both cases, P and N, okay. Of course, beta P, beta N by 2, beta P by 2. But there is no term which is V0 dependent. Is that correct? There is no term which is V0 dependent. So at that input, output falls suddenly. Okay. Beyond this, now the opposite will occur, Tp will enter saturation, Tn will enter non-saturation, and finally it will switch it off. The transfer characteristics of a CMOS is something like this, which is closer to ideal switch, Therefore, everywhere, instead of using N-channel CMOS, N-channel inverters or P-channel inverters, we'll use CMOS inverters. So all the circuits, 99%, which you use in your labs or in systems everywhere in the world are CMOS based because they are closer to better switch activity. Is that correct? Logic wants 0, 1. So we can create better switching, and therefore we say CMOS circuits are ideal for switches and therefore ideal for digital logic. Okay. This is why CMOS inverters are extensively used everywhere. Once you know inverter, digital circuit will tell you can create any other function, NAND, NOR, XOR, adder, multiply, you can make any circuit at the end of the day if you know your inverter design correct. Okay. If you know this, you can build any system ahead. That's why any digital hardware can be created by designing a proper inverter for you. Is that clear to you? Is that clear? This finishes the MOSFET activities altogether. We have seen almost everything which is related to MOSFET. Some way we bypass some things because we didn't want to go too detailed. But basic ideas are communicated. Basic equivalent circuit is used for what? For analog signal in small amplitude, small signal analysis. So the equivalent circuits are useful only in analog circuit because they have been derived for small signal omega based system. Digital circuit requires switching. So we go for this kind of characteristics, and remember this is called large signal analysis. Why? Signal is moving from 0 to VDD, no small 10 millivolts, 0 to 5 volt, 0 to 3 volt. Okay. So the analysis is specifically called large signal analysis. Is that correct? Okay, so this finishes the MOSFET, and I took MOSFET ahead of BJT. For what reason I said? As 99% systems are on CMOS, you should better know MOSFET better these days compared to BJT. But MOSFET contain PN junctions and it also contain field effect. Okay, so I thought first at least I should do PN junction, and then I should do field MOS capacitor, and then merge them together to get first device, which I said is MOSFET. What is analog advantage of a MOSFET otherwise? The input impedance is only capacitive. So at lower frequencies it is very large impedance. Is that correct? So connection is much easier compared to BJT, whose input impedance is mostly resistive and few kilo ohms. Is that correct? The biggest advantage MOSFET provides. The other thing is size-wise, BJT will be larger for the same performance compared to a MOSFET. Is that clear? Therefore, for density, what is density means? Number of transistor per unit area will be always orders larger for MOSFET. Orders mean 10 times, 100 times compared to BJT circuits. Third, power dissipation in MOSFET is extremely low because typical currents is in microamps, whereas in the case of BJT it will always be milliamps. So the advantage of power is automatic in the MOSFET. Only thing people felt, since the current is smaller, so the speed will be smaller. No, speed is achieved through other means to some extent, and we do go to similar speed, if not better speeds than BJT. So only place where BJT will still find use is high speed, super speeds, okay. But then what will you spend on? Power. So essentially you are saying power and speed goes opposite to each other. Higher the speed, higher is the power requirements. Okay. So if you are taking somewhere in the space, something like shuttles, there you may survive speed by some other technique, this power, but you will have to see that your speed of this, because the response time has to be faster. Okay. So a microprocessor is normally designed for very high speed performance, but at higher power dissipation. Or even larger area they don't care because it should perform. So the word performance always goes with speed, high performance, high speeds. Okay. So most circuits we require are high performance, but not necessarily always. Then the other is low power, and third is low standby power. When the circuit is not performing, the static power loss should be minimal, and we say low power, low standby power. Okay. So the circuits are designed on these three: low standby, low power, and high speed means high performance. Is that correct? MOSFET try to meet most of it, if not all of it. Okay? And therefore, everywhere you will find MOSFETs are extensively used. We will stop here today. We may go for JFET tomorrow.